Well, we have atomic masses listed for each element on the periodic table. And like we just looked at chlorine, and if we look at chlorine on the periodic table, it says 35.453 underneath. We just saw an isotope of chlorine that had 30, no, that was potassium. Never mind. My train of thought just had a wreck and jumped the tracks. Okay, mass numbers are nice whole numbers, right? But the numbers under the symbols on the periodic table are not nice whole numbers. That's because they are average masses. So we looked at neon, and there were 3 different isotopes. The most common one was neon 20, but there was also neon 21 and neon 22. And so the average mass of a neon atom is 20.1798. That's the average. Now, it's not possible to take all the atoms and weigh them individually and add them up, like we would do a normal average. You take the mass of each thing, add them together, divide by the number of things. We use what's called a weighted average. Oh, this is why I was thinking chlorine, because it's right here in front of my face. Chlorine has 75.77% chlorine 35 and 24.23% chlorine 37. The mass of each of these isotopes in the atomic mass unit is very close to its mass number. It's not exactly the same, though. It's really close. So this is almost 37, and this is almost 35. 75% roughly are this one, 24% are that one. We can't just add them together and divide by 2. So what we do is we take this fractional abundance, we take this percentage and divide by 100 to make it into its decimal equivalent. We multiply by the mass of that, and then we add the other decimal equivalent of the percentage times its mass, and that gives us 35.45 atomic mass units. That's the average mass of a chlorine atom. Now, there is no atom of chlorine that actually weighs the average, because there's 2 kinds. There's ones that weigh 35 and there's ones that weigh 37. But the average is closer to 35 because more of them are 35. And we never do things with 1 or 2 atoms. We're always dealing with gazillions of atoms. So the average mass is actually what's useful to us. So here is that same idea in more of a general form. To find the atomic mass, you take the fraction of the first isotope times its mass, the fraction of the second isotope times its mass, the fraction of the third isotope times its mass, and you add them all together. Because we're using fractions, we don't have to divide by anything at the end. Let's do an example. Magnesium has 3 naturally occurring isotopes. It gives us the masses, and it gives us the natural abundances. Let me get out my calculator. Calculate the atomic mass of magnesium. Now, could we just look on the periodic table? Sure we could. But on exam 2, there will be a question with a made-up element that is not on the periodic table, and so you'll have to do the math. We'll use the periodic table to check ourselves. So the first one is the 78.99%. So dividing that by 100 to make it into a fraction, 7899. So times its mass. So the first one is 23.99 atomic mass units. I think if I had an emu, I would name him Amu. Amu the emu. My mind wanders. 10%. Dividing that by 100, I get 0.1000 times the mass of the second one, 24.99 atomic mass units. plus the last one, 11.10%. So that's 0.1110 times the mass, 25.98. And then I just put these into my calculator. Most calculators will understand this without you saying anything special to them. 0.7899 times 23.99 plus 0.1 times 24.99 plus 0.111 times 25.98. Great syntax error. Excuse me while I argue with my calculator. Okay, so I'm getting 24.607371. Anybody else get that? Yes, no, no? It's entirely possible that I just completely screwed that up. So this is something, I think I've said this before, it's always a good idea to do the calculation twice because it is so easy to mess up like I just did. I wish I could say I did that on purpose, but alas, I did not. I think I know what happened. There, that's better. 24.332481, yeah. So if you do the calculation twice and you get the same answer, you probably punched it in correctly, or you're consistent in making mistakes. If you get it two different answers, go for best 2 out of 3, and that can save you points. So the unit here would be atomic mass units. Significant figures here, we've got multiplying and adding mixed together. Those can get messy. Usually you can just look at how many sig figs did the individual masses have and keep the same. So we would round this to 24.33 atomic mass units. Any questions? Again, this is not complicated math. The hard part is just remembering what to do with the stupid numbers. Okay?